Before the first second, the Planck satellite, operated by the European Space Agency between 2009 and 2013, produced the most detailed map of the cosmic microwave background radiation ever made. The cosmic microwave background is the thermal afterglow of the Big Bang, photons that have been traveling freely through space since approximately 380,000 years after the universe began, when the plasma of the early cosmos cooled enough for electrons and protons to combine into neutral hydrogen and allow light to move unimpeded for the first time. The Planck map shows temperature variations across this ancient light at a precision of 1 part in 100,000. These variations encode the initial conditions of the universe, the density fluctuations that seeded every galaxy, every star, every planet, and every observer that has ever existed. The map is extraordinarily detailed. It confirms, with a precision that leaves essentially no room for meaningful doubt, that the universe we inhabit began approximately 13.8 billion years ago in a state of extraordinary heat and density and has been expanding and cooling ever since. This is the data. This is what we know. And it is precisely what we know, followed to its logical conclusions. That generates the most disturbing set of questions in all of science. Questions about what caused the Big Bang, what preceded it, and what the answers to those questions imply for the silence of a cosmos that should, by every calculation we can perform, be filled with the signals of civilizations that have been asking them for billions of years, longer than we have. This is where the terror begins. Because the question of what caused the Big Bang is not merely a cosmological curiosity. It is directly connected to the Fermi Paradox through a chain of reasoning that the scientific community has been reluctant to assemble in its complete form. The chain begins with the Planck data and ends somewhere that most researchers prefer not to look directly. What follows is an account of that chain, constructed from the data and the 8 most serious theoretical frameworks that attempt to explain the origin of the universe, arranged not by scientific consensus, but by the particular implications each one carries for the question of why the cosmos is silent. The first theory is the quantum fluctuation from nothing, most closely associated with the work of Alexander Vilenkin and developed in detail through the 1980s and 1990s. The theory proposes that the universe emerged through a quantum mechanical process analogous to tunneling, in which a system passes through an energy barrier that classical physics would prohibit it from crossing. Applied to cosmology, this means the universe tunneled into existence from a state of absolute mathematical nothingness, not empty space. Not a quantum vacuum with virtual particles, but genuine nothing. No space, no time, no energy, no physical law. Vilenkin's mathematics describe this process using the wave function of the universe, a quantum mechanical object that assigns probability amplitudes to different possible universes. The calculation yields a specific probability distribution for the initial conditions of universes created by quantum tunneling, favoring universes that begin small and then inflate rapidly. The Planck satellite data is consistent with this prediction. The temperature fluctuations in the cosmic microwave background match the spectrum predicted by inflationary models that could have followed a quantum tunneling origin. The numbers fit. What the numbers also imply, and what Vilenkin has stated more directly than most cosmologists are comfortable with, is that quantum tunneling from nothing is not a one-time event. If the process occurred once, it occurs continuously. New universes are constantly tunneling into existence from the quantum nothing, each one independent, each one beginning fresh with no connection to any other universe. In this framework, the Fermi Paradox is addressed by radical temporal and spatial isolation. Every universe that exists began fresh, with no accumulated history from any prior universe. There is no mechanism by which intelligence from one universe could influence or communicate with intelligence in another. The silence we observe within our universe tells us nothing about what might exist in other universes. And the civilizations that should be filling our own universe with signals, the civilizations predicted by the Kepler exoplanet data and the Drake equation, are not explained by the quantum tunneling framework. Their absence remains unexplained. The framework accounts for the origin of our universe but does nothing to resolve the silence within it. The second theory is eternal inflation, which emerges naturally from the inflationary model that the Planck data so strongly supports. Cosmic inflation, proposed by Alan Guth in 1980 to explain the flatness and uniformity of the observable universe, posits that the very early universe underwent a period of exponential expansion driven by the energy of a quantum field called the inflaton. The Planck satellite data provides strong support for inflation through its measurement of the spectrum of temperature fluctuations in the cosmic microwave background, which matches the predictions of simple inflationary models with high precision. But inflation, once started, does not stop everywhere simultaneously. Quantum fluctuations in the inflaton field cause inflation to end in some regions while continuing in others. The regions where inflation ends become bubble universes like our own. The regions where inflation continues to keep expanding, producing more bubbles endlessly. In eternal inflation, the inflating background spacetime has no beginning and no end. Our universe is one bubble among an infinite or near infinite number of bubbles, each with potentially different physical constants, different particle masses, different force strengths, and different initial conditions. The Fermi Paradox in the eternal inflation framework acquires a dimension that is not resolved by the framework itself. Within our bubble, the physics of star and planet formation, the abundance of potentially habitable worlds measured by Kepler, and the timescales of galactic history all predict the existence of civilizations far older and more advanced than ours. Eternal inflation explains how our bubble came to exist, but does not explain why our bubble is silent. The bubbles are causally disconnected from each other, separated by inflating spacetime that nothing can cross. But within each bubble, the same physical laws produce the same prediction. Civilizations should exist and should be detectable. The silence within our bubble is not explained by the existence of other bubbles outside it. The third theory is the cyclic model, developed by Paul Steinhardt and Neil Turok as an alternative to conventional inflationary cosmology. The cyclic model proposes that our universe is a three-dimensional brane in a higher dimensional space, and that a parallel brane exists nearby, separated by a small extra dimension. The two branes are attracted to each other and periodically collide, with each collision experienced as a big bang on both branes. Each cycle lasts approximately 1 trillion years. The collision generates the hot, dense initial conditions of a new cosmological cycle. In this model, the Big Bang was not the beginning but a transition, one of an infinite or near infinite series of collisions that have been occurring for an incomprehensible span of time. The Planck satellite data places constraints on the cyclic model. The model predicts a specific spectrum of primordial gravitational waves that differs from the prediction of simple inflationary models. Future gravitational wave detectors may be able to distinguish between them. What the cyclic model implies for the Fermi paradox is the most mathematically disturbing of all the frameworks. If cycles have been occurring for an infinite or near infinite time, then civilizations have had an effectively infinite number of opportunities to arise, develop, and potentially persist across the transition between cycles. If even one civilization in the history of infinite cycles has ever found a way to survive or influence events across a cyclic transition, its presence should be detectable in our current cycle. The absence of any such presence, the complete absence of any artifact, signal, or modification of physical reality that cannot be explained by natural processes, implies that no civilization has ever survived a cyclic transition. The mechanism that prevents this survival appears to operate with perfect consistency across an infinite number of cycles. Whatever that mechanism is, it applies to every civilization that has ever arisen in the history of an infinitely old universe, and it will apply to us. The fourth theory is the black hole cosmology proposed by Lee Smolin in the 1990s, which suggests that new universes are created inside black holes, with physical constants similar but not identical to the parent universe. The Planck satellite data cannot directly confirm or refute this model, but the observed abundance of black holes in our universe is consistent with Smolin's prediction that universes are selected for high black hole production. The Fermi paradox implication of black hole cosmology depends critically on whether information or structure survives the formation of a child universe, and whether civilizations that learn to create black holes might in principle seed child universes with intentional information. The silence we observe in our universe in this framework could mean that no civilization in our universe has yet developed the technology to create black holes intentionally, or that the information transfer across the black hole boundary is not possible in the way Smolin's framework might suggest. What it cannot mean within the framework is that civilizations do not exist. The physics of our universe permits their existence. The silence remains unexplained. The fifth theory is the string theory landscape, which proposes that the equations of string theory permit approximately 10 to the power of 500 possible vacuum states, each corresponding to a universe with different physical constants. The specific vacuum we inhabit was selected not by a unique physical mechanism, but by anthropic reasoning, the observation that we could only exist in a vacuum compatible with our existence. The Planck satellite data is consistent with this framework insofar as the measured value of the cosmological constant, which is inexplicably small, is more naturally explained by anthropic selection from a large landscape than by any known physical mechanism. The string landscape's implication for the Fermi Paradox is that the physical constants of our universe, which permit stars, planets, chemistry, and life, are not uniquely determined, but are one configuration among many. The same anthropic reasoning that explains why we find ourselves in a habitable universe applies equally to every civilization that exists in any universe. Within our universe, the constants that permit the existence of every other civilization as well. The landscape explains why our universe is habitable. It does not explain why our habitable universe is silent. The sixth theory is the Hartle-Hawking no-boundary proposal, in which the universe has no boundary in time and the question of what came before the Big Bang is ill-formed, analogous to asking what is south of the South Pole. The Planck data is broadly consistent with the predictions of the no-boundary proposal. The implication for the Fermi paradox is the starkest of all the frameworks considered here. If the universe has no prior state, if it is a self-contained mathematical object that simply exists without cause, then the silence of the cosmos cannot be explained by appealing to conditions outside the universe. Every possible explanation for the Fermi paradox must be found within the universe's 13.8 billion-year history. And within that history, the data says civilization should exist and should be detectable. The no-boundary proposal removes the possibility of explaining the silence by reference to prior cosmic states or external causes. It forces the conclusion that the explanation lies within the physics and history of the observable universe. The most consistent explanation within those constraints is that civilizations do not survive to the point of galaxy-spanning detectability. The filter is inside the universe. The filter operates on civilizations after they reach a specific developmental threshold. The threshold has not yet been identified with certainty, but the developmental characteristics of the civilizations that exist at the boundary of detectability and then go silent can be inferred from the data. They have radio technology. They have nuclear weapons. They have or are developing artificial general intelligence. These are the characteristics of a civilization at the threshold. These are our characteristics. The Planck data cannot tell us what caused the Big Bang in the no-boundary framework, because the question has no answer. What it can tell us, combined with the Kepler data and the SET, the first silence, is approximately where on the developmental scale the filter operates. The uncertainty in that estimate is not large enough to be comforting. The seventh theory is the simulation hypothesis applied at the cosmological level, which proposes that the Big Bang was the initialization of a computational process, that physical reality is the output of a calculation running on hardware that exists outside our spacetime, and that what preceded the Big Bang was a programmer, a decision, and a set of initial parameters. The Planck data is consistent with this framework in the specific sense that a simulated universe would have the same observable properties as a physical universe of the same age and composition. The simulation hypothesis makes the fewest additional assumptions of any framework considered here, in the sense that it requires only that computation is possible outside our universe and that someone or something with the capacity for computation existed before our universe began. The Fermi paradox in the simulation framework acquires a character that is different from all the physical frameworks. If the universe is a simulation, then the silence of the cosmos could be a design choice rather than a physical consequence. Other civilizations might exist and have their signals suppressed by the simulation's parameters, or the simulation might have been initialized with only one technological civilization as a deliberate experimental condition. Or the silence might be the expected result of a simulation that was initialized to run until a specific event occurs, and every civilization that has preceded us in the simulation's history has either reached that event or been prevented from communicating by the simulation's design. What distinguishes the simulation framework from the physical frameworks is that it generates no testable predictions that differ from those of a purely physical universe. Every observation we make is equally consistent with a simulated and a non-simulated universe. The framework is unfalsifiable, but unfalsifiability is not the same as incorrectness. And the silence of the cosmos is equally consistent with a simulation designed to be silent as it is with a physical universe in which civilizations consistently fail. The eighth theory is the most recent and in some respects the most mathematically constrained. It emerges from the measurement of the Hubble constant and the tension between the two independent measurements of its value. The cosmic microwave background measurement, which the Planck satellite performs, and the local distance ladder measurement, which uses Cepheid variable stars in type 1a supernova, disagree by approximately 9%. This disagreement has not resolved itself as measurements have become more precise. It has gotten worse. The most natural explanation for a persistent, growing disagreement between two physically independent measurements of the same constant is that the constant is not constant, or that the physics of the early universe differed from the physics of the late universe in a way our current models do not capture. The most disturbing version of this explanation proposes that a phase transition occurred in the universe's history, a change in the properties of dark energy or some other fundamental field that altered the effective value of the Hubble constant between the early and late universe. If such a phase transition occurred, its timing would be determinable from the data, and its implications for the habitability of the universe at different epochs would depend on how it affected the stability of physical constants more broadly. A universe that underwent a phase transition in its recent past could be a universe in which the window for the development of technological civilizations is narrower than we currently assume. The phase transition would act as an additional filter, one that operates at the cosmological level rather than the civilizational level, eliminating not individual civilizations but entire epochs of potential civilizational development. The silence of the cosmos in this framework is not the silence of civilizations that failed. It is the silence of a universe that has been, for most of its history, less habitable than it currently appears. And the civilizations that have arisen in the current habitable epoch, which is the epoch we inhabit, have not yet had time to expand to the point of galactic detectability. They are out there. They are young. They are just at the point we are at. And if the phase transition that preceded the current habitable epoch repeats, or if the Hubble tension is evidence of an ongoing change in the universe's fundamental properties, the current epoch of habitability may be narrower than 13.8 billion years of cosmic history suggests. We may be not at the early dawn of a long habitable era. We may be near the end of a brief one, and the civilizations that arose before us in this epoch have had the same amount of time we have had, and are at the same developmental stage we are at, and have not yet managed to cross the galaxy, and the Planck satellite data tells us why not. In the most indirect and unsettling way possible, by showing us a universe whose history encodes not just the conditions for our existence, but the conditions for our limitation, written in the oldest light there is, in temperature variations of 1 part in 100,000, waiting patiently for someone to read them correctly, which we have now done, and the reading is not what we hope to find.